Following, we will be more focusing on technical details. Next, please allow me to have two colleagues from Intel, Xie Huawei and Tan Zhenfeng, to share with us virtual and Vhost technology. Good morning, dear developers. Today, I would like to talk about virtual and Vhost background and how we will do the development and the DPDK in user space. Firstly, I will talk about the background. Second, I will talk about how VirtIO is applied in NFV and the cloud. What are the challenges and the solutions? Lastly, we will have my colleague Tan Zhenfeng introducing how to have a fast, accessible Internet port. Firstly, what is the background and the definition of VirtIO and Vhost? VirtIO is a de facto para-virtualization standard for communicating with virtual machines efficiently. It has both front-end and back-end. The back-end is run on the host virtual machines. The back-end has two sides. We have the emulation of the device. The other is responsible for the message receive and sending. Vhost is responsible for the backend, while VirtIO is for the front end to forward all the information, to switch packets to the backend. The switch will be doing the data transmission between the vSwitch and the DPDK. In data center and transforming network revolution, NFV and cloud are two of the major trends. The definition of cloud is very familiar to us already, so I will not spend further time. But for NFV is to virtualize the specific application and the software. So according to your needs, we can dynamically generate, orchestrate, or eliminate. Virtualization is to run network features in the virtual machines, and we call it VNF, Virtual Network Functions. For NFV and cloud, what are the main challenges? The main challenges are how to provide stable and efficient data packets. VirtIO as a semi-virtualized standard, we can provide the most hardware, can support dynamic migration. It is the first choice for NFV and cloud. On the left-hand side, on the diagram, you can see the two typical scenarios. In the lower tier, we have the infrastructures, including commodity x86 servers, QEMUs, packet processing pipelines, as well as other accelerators. We also have the open source. Moving forward, we have DPDK virtual switch. And affiliated to that, we have the physical port and the backend port, as well as Vhost port. In the cloud scenario, we have the tenant virtual machines. In the tenant virtual machines, we have a socket app, networking stack, and a socket application. Regarding networking virtualization, it's a typical service virtualization. The data packets will go through different virtualized features. Applying VirtIO to NFV and cloud, what are the main difficulties? I have listed most of the difficulties in the two types. First of all, stability. Second is performance. Regarding stability, we have north to south performance and Vhost reconnect performance, as well as east to west performance. For north to south performance, we provide DPDK polymer driver to DPDK and keep optimizing the features. These are the front-end performance. For back-end Vhost, we are also providing support. We are trying to use AVX to accelerate Vhost and to achieve delayed copy, and to achieve zero copy between virtual machines and Vhost, as well as to reduce the memory copy in between. Focusing on cloud and the big packet performance, we support Vhost technology. For east-to-west performance, between virtual machines, if there are large traffic of data transmission, we will establish a fast path, which is a VM to VM fast path. The second issue is about stability. Why stability is a difficulty? It's because DPDK-based virtual machine is a user layer. If the user application crashed or if it is killed, it will significantly be a disaster for the service provider.
The VM may lose contact with the outside world, so we provide the Vhost connector technology, which supports the rebooting of Vhost and restarting the connection with the front end and also other recovery features. So now I'd like to talk about VirtIO's optimization, PMD optimization, Vhost, AVX, and also other features. Before I touch on these topics, let's first look at the history of the VirtIO development. It started in about year 2013 and has been about 3 years. I will not go into details about every feature though for the interest of time, but first about the front-end drive and then the Vhost, QEMU host, which provides data to the front end but still relies on kernel module. So in 2014 we provided we were supported by Vhost fields, so we could use Vhost to have data exchange with the front end, and also we achieved zero copy and other multiple features, and then we encapsulate it into a library so as to be integrated with the adapter, and then in 2015 QEMU officially supported and then we supported the Vhost. And then we did the layout front-end drive optimization so as to support the migration, live migration, and then GEP company encapsulated it into a driver so as to better facilitate the integration of the two. So now let's look at the first topic, the front-end optimization. First of all, let's look at the VirtIO packet receiving and sending process. First is the front-end drive. It has this free descriptor list. The front end to receive data must first allocate one descriptor and then modify its varying so that it points to the descriptor, and then it modifies the guest area and then updates the index and notify the Vhost. And after notification, the Vhost need to take the content of the available room and then use the index, read the descriptor from there, and read the address info and translate the address, and then have data exchange between guest buffer and host buffer. In terms of optimization, there are two typical issues with this process. First of all, the first issue is VirtIO has to modify the varying frequently, and the host has to read it frequently, so that it means the transmission between the two processing units, and the transmission may be very time consuming. As we know, the one cache has latency of 3 cycles, and LLC log test cycle is 34 cycles. And for Vhost to update and read it has to read up to more than 60 cycles. And what's worse is that for such long latency, they cannot be extended because the descriptor reading depends on the avail ring reading, so it's dependent. However, it can be mitigated to some extent by some operations. And another issue is that because available ring to descriptor ring has this indirect index, so we cannot use the following command to accelerate it. For these two issues and for the actual situation of the network, we propose the optimization as follows. That is the fixed available ring. First, let's look at the RX process. At the initialization stage, we initialize the available ring so as to let each ring point at the fixed descriptor. In the entire operation, it doesn't change. So when the front end receives and sends packets, it just need to modify the descriptor ring. That has 3 benefits. First, the front end drive doesn't need to allocate the descriptor, and second, because the available ring is not changed during use. So in optimal situation, it will stay in the own cache of the virtual server and so on, and its latency is only 3 cycles. And thirdly, because the available ring is not changed in terms of content, only the descriptor ring is changed, so that we can use the command to accelerate the processing. And let's look at the sending process. It's similar to receiving, only we need to use an extra descriptor to point at the virtual metadata and net header. And also, for the sending process, this process is a little bit limited. The DPDK buffer has to be single segment, not a list. And next, let's look at the optimization result. We use benchmark to test it, and we can see that the performance is improved 2 or 3 folds. Now, this optimization is already in DPDK. And next, because VirtIO is a generic or commercial virtualization port, so can we have better ring layout for the network? That's a question we have been thinking. The ring layout that's convenient, that's friendly to what we call communication and has better acceleration and so on. And the next topic, the Vhost TSO. First, what is TSO? TCP segment offloading. It's an acceleration technology, as we know. TCP, before exchange data with the other end, first we'll negotiate the MS size so as to make sure that it doesn't exceed the MS. If the packet is larger than the MS, then the TP layer has to slice them and repack them. That's a very CPU-intensive operation and will reduce the performance of the protocol station. Now the net card supports the TSO technology. It supports slicing, and with the support from TSO, we can delay this slicing process so that until the big packet receives the net card drive, we can have them sliced. And in the virtualized environment, because the Vhost, the front end and back end are realized by software, not hardware. So how do we deal with that? VirtIO sends packets to two destinations. One is in the host, that is the network hardware, and the second destination is to other virtual machines of the clients. So if it has to go through the host network hardware and it supports slicing, then we can use the host network to do it. Let's look at the first scenario. Let's look at how it is realized. In the user VM, there's the segmentation offloading so that the packets can receive the virtual driver, and it's not sliced. And the virtual driver doesn't actually slice. It only at the metadata meta header it marks the domain for it. In the Vhost, after receiving the packet, it will recognize the need for slicing as well as the need for offloading that will be generated in the host and buffer, and after it is sent out by a network card that will instruct the reconnect card to actually do it. It's quite simple. And about TSO, in VM to VM, how it is realized. It's just like the previous process. In the Vhost, in the host buffer, it marks the need for slicing. And then, if the host and buffer has the destination of another VM, then in queue it will be recognized. This need will be recognized. There's no need for slicing. And after realizing that it is from another VM of the same host, it is a reliable path. There will be no corruption of the data, so that it will label it as legitimate, and in the virtual database it will say this is a legitimate packet and send it directly to the second virtual queue. DPDK realizes performance like this. The left hand are three VM, the VM to physical network TSO, and the right hand side is the VM to VM TSO. As you can look at this box, DPDK supports it is the different performance, and in the middle is the DPDK performance. We can see that the performance has been improved significantly. Why is DPDK? Why is the kernel TSO similar? Because they have achieved the 10 GB speed limit. If we use a 40 G net card, then DPDK TSO may have some difference. And next is Vhost reconnect. Just now we said we wanted to have the reconnect technology because for service provider it's very important. It's a virtual switch for user space, which may have accidents or get killed accidentally. And the solution is rather simple, however, it requires some QEMU changes and other little techniques. Let's take Vhost for instance. That is the whole client and QEMU as the server, but we can do vice versa, QEMU as the client and Vhost as server. There may be some small differences, but intrinsically they are the same. So the Vhost will connect to the QEMU server as a client, and then QEMU will collect the information of the VM as well as the it will directly operate the ring and have packet exchange. However, now if Vhost is crashed or is killed, QEMU will detect this event, and then QEMU will need to make some changes so that QEMU can establish a new connection, and then we restart Vhost and start the new connection. QEMU will have the virtual as well as other information and resend them to Vhost. And next, I want to say that this looks like a simple process. However, how to recover the status of VirtIO? There may be three status. One is that it's in the memory of VirtIO itself. So the available index and user index will not be lost under such status. And another status is the support of the features. Because negotiating the features, hotel driver is, if it's not reloaded, the negotiation will not start again. So we need to keep and resend them. And a third status is Vhost. It's maintenance.
这些状态就是 Vhost 的本地维护。
So we will do the localized maintenance to the Vhost. This status is not upgraded efficiently in real time to QEMU. If Vhost crashed, the status will be lost. The typical condition is last user index. If we just blindly have the last user index set up as 0, and it will make a chaotic systematic reaction. But there is one absolute solution for that. If QEMU is having the front end to do reset again and to have it defaulted, that is a long-term solution. The second time, it will not be able to solve the existing kernel existing in Windows and Linux kernel issues. We have analyzed the upgrade status of Pring, and we have a solution. For the last user index, we can have it upgraded. We have it restored as the index like this. This solution can perfectly be a good solution. For the Vhost send packets, some of the packets will be resent, but that is no big issue. For east to west performance issue, let's give introduction as well. So for all of the packets, they will need to go through different VMFs. Between the virtual machines, there is a lot of transactions. Logically speaking, there are communication between the virtual machines, but they all need to go through the Vhost. For example, between virtual machine 1 to virtual machine 2, we need to have the packets from VM1 and then go through Vhost and then send it to virtual machine 2. Out of Vhost, it is not only doing packet processing, it is also capable of doing packet I/O. So virtual switch will become a centralized bottleneck. To the service providers, we all would like to have virtual switch occupy as less resources as possible. The most ideal way is to occupy only one processing capability. So under this condition, if you have so many virtual machines, it will become a very much centralized bottleneck. Between the virtual machines, it is possible to create the faster data path, so the communication between the virtual machines doesn't have to go through Vhost. That is a natural approach that we come in mind. We have analyzed the virtual I/O configuration. As we all know, DPDK, Vhost, user server. it has all of the information of the virtual machines and the memory information. Let's take VM1 and VM2 as an example. It has all of the memory information of VM1 and VM2. If the vhost user server have VM1 and VM2's information extended to the protocol and send it to VM1, VM1 will be mirroring without mirroring, and it can access to VM2's memory. Then VM1 will be capable of sending the package to VM2 directly. For our idea, in VM1, we have a vhost PCI device. The vhost PCI device is used to receive the other side's memory information and VirtIO information. With the vhost PCI device, we will be able to develop a DPDK engine and to send the packets directly to the counterpart's virtual machine 2. So this is the final landscape and layout. In VM1 and VM2, we have the VM devices. In the VM, we have the vhost PCI device. The vhost PCI device is used to mirror the device of VirtIO in virtual machine 2. The package sent by virtual machine 1, if it's not sent through the vhost, it will get into the queue receivable for virtual machine 2 automatically. Under such a model, between virtual machines, the communication doesn't have to go through vhost, so the pressure of vhost is significantly reduced, but we can also find a solution for the centralized bottleneck we have mentioned earlier. For this topic, we are still looking for better solutions. In the next couple of weeks, we will have a QEMU community. Of course, the model had one issue. If VM1 can get access to memory of VM2 directly, it will bring some security issue. Intel has the new virtualized tools, which is the switching. So when VM1, it can have two lists. The first VNF is its own table. The second EPDA table can be used to mirror the memory of VM2. Each time VM1 needs to send the package to VM2, we will just switch between. In this way, it will be capable of get access to the memory of VM2. Of course, the second table is a hypervisor, so it can visit its own memory as well. After switching to EPDA table, when the switch happens, we will only ensure several code pages can be executed, supported by the host. So when in EPDA, it can only execute what's supported, which is to send and copy the data from VM1 to VM2. In this way, we will be able to avoid the security issue. VM1 can only rely on the data supported by host. It will not be able to read and write VM2's memory. In this way, we will be able to solve the security issue. Next, I want to give a quick introduction to our future work. We have a completely new ISA to support call-to-call transformation, including the cache transmission. The typical issue may include, in all of the switches, vhost get data of VM1. It may modify the buffer. Buffer content will be migrated to vhost cache. So vhost call doesn't have to process this information. It can use the latest instruction set. So the cache profile will be sent to the last layer cache and save the space for the actual process. If there are other data needs to be processed, the data migration can be reduced regarding the efficiency. Only 30 cycles. Using the legacy ones, if you don't keep away the data, it will take around 60 cycles. Second thing we will do in the future is to support Vhost delete copy. From VirtIO to Vhost copy, we will have it delayed until it really needs to happen. When the data gets to the physical card of Vhost, we will be able to achieve 0 copy. When it arrives in the other virtual machines, we only need to do 1 copy. So between virtual machines, we can reduce 1 copy. From the virtual machine to the physical card, we can achieve 0 copy. Next, we will also support Vhost AVX to accelerate. We are also trying to use FPGA to do the acceleration as well. Next, I will talk about what we have to do for containers.